identity matrix. Identity matrix. So this identity matrix is a square matrix. So we always talk about the square matrix, yeah, when saying this identity matrix. So it is 3 by 3 or 5 by 5 and so on. And then you may know it already, but this diagonal entry is all ones, and then other entries are all zeros. Okay, so in this case, let's see. So this identity matrix is has an important characteristics, like, so given this matrix, and then suppose we are given this vector, and then this matrix and this vector multiplication will give the exact same result as the original vector, right? So that is the one important characteristic of this identity matrix. Okay, and then there is some interesting properties in the matrix and vector multiplication. So given this sum of these two vectors and then multiplied with the matrix A, and then it can be distributed in this manner. And then we first do the scalar multiple. So in this case, please note that this guy is a column vector because it's written in boldface, and this is in a plain font, and so it is a scalar, right? So it's like matrix A here, matrix A here, and then some scalar and some vector, right? So in this case, so this scalar multiple of this vector u can be reordered in a way that this matrix times the vector multiplication, and then we just do the scalar multiple on the resulting vector. Okay. And then I will skip the proof. Okay, so that was it for this chapter 1.4. I close the quiz, okay? Okay, so let's move on to the next chapter. So the next chapter is about the solution set of a linear system. So in this case, we first think about some special linear system called the homogeneous linear system. So we think of a linear system, okay, but especially the homogeneous linear system has this form, okay. So this is just a standard linear system, but on the right hand side, the vector b is given as a 0 or origin, okay. So that is called a homogeneous linear system. But let's look at whether we have a solution or not in this case, okay. So in this case, so let's look at this linear system as a vector equation. Suppose A has like these 3 columns. Then their vector equation form will have a linear combination of these 3 vectors on the left hand side. And then what is our right hand side vector? So it is all 0, right? And then in this case, in terms of the whether we have a solution or not, if our b vector is belonging to the span of a1, a2, and a3, okay, where this guy is a1 and a2 and a3, okay. So if this is the case, or if this is true, and then this is when we have a solution, right? But here in this case, b vector is all 0. right? It's just a 0 or origin. So this origin is always included in the span of like any vectors, right? So yeah, imagine that once we have a one vector, okay, just one vector, and then it will already contain 0 or origin, right, in our span, right? So in this case, the solution will always exist. And what will be, what will be one of such solutions in this case? So how can we generate this 0 vector? By carefully, changing or carefully determining those green part or linear combination coefficient. Okay, what will be our, one of our solution? It will be just 0, right? So we just set the linear combination coefficient as all zeros, and then it will just easily generate the 0 vector, right? So 0, 0, 0 is one solution. Okay, so here, so again, this is true. Does the solution exist? That means our solution will be either a single solution, I mean unique, or infinitely many solution, right? Yeah, so in this case, we will study when our solution, I mean when we have infinitely many solutions in this particular homogeneous linear system, where we have 0 on the right hand side. Okay, so this is something that we will study in this chapter. Okay, so in this case, this particular solution of all zeros is called trivial solution, because it's really, literally trivial and quite easy to obtain, right? Okay, and then so this is one example. Okay, so once we change it into echelon form, so we will have all coefficients here and then 0 here, right? Okay, and then let's look at this example, and then so this is our echelon form or reduced echelon form matrix. So here we have a pivot here and here, right? So again, in this particular example, this is corresponding to homogeneous linear system because we have all zeros, and then we are trying to see if this linear system has either unique solution or infinitely many solution, which is our case in this example. Okay, so that is our question to answer. Okay, so this is our reduced echelon form. So looking up and bottom, so we will see our zeros along this pivot entries, and our pivots are ones, right? So this is a reduced echelon form, and then once we write our solution, we reconstruct every row. So this row is reconstructed or converted into this equation form, right? And then the second one will have this guy, and the third equation will have this guy. And then the next step that we did was we moved all the free variables to the right hand side, right? So here, what is our free variable? So we have, so we have x1, x2, and x3. So we have a 3 variable, and then x1 and x2 are basic variable that contains our pivot, right? And then x3 was our free variable, right? And then once we obtain this, okay, and then we move our free variables all the way to the right hand side. So in this case, this guy will be moved to the right hand side. Okay, and then we obtain this. x1 will be equal to this, and x2 will be 0. x3 is our free variable, right? And then here we will use just one simple but really important trick. Okay, so let's just form our solution vector, instead of just representing our solution as this individual equations. Okay, so in other words, let's think about our solution vector as this form: x1, x2, and x3 as just a column vector. Okay, and then x1 will be represented in terms of some free variable, right? Because we moved our free variable to the right hand side, right? And so from here we bring this guy here, right? And x2 is 0, right? And why was it 0? Okay, so in this second equation here, that contains the pivot for x2. So that didn't have any free variable, right, corresponding to our x3, or it didn't have any constant values, right? So here the point is, suppose we started from all 0, right, all zeros, and then this was our reduced echelon form, where we have 0 columns on the last column as the last column. And then we did a row reduction step by step, right? But what about this last column? It will always remain as zeros, right? Because we just multiply one row and then add or subtract from the another one, okay? And then from this process of our row reduction, these one will remain all 0 all the time, right? So after we change it to reduced echelon form, we can see that the zeros are still remaining here, right? So that is the point. That is one important point. Okay, and then yeah, back to this guy. Yeah, x2, it didn't have any free variable or any constant value. I mean, in other words, it has a 0 constant value, and thus x2 is 0. Okay, so x2 can be represented as 0, and then what about x3? So initially in our solution, represented in this form, so in this case, x3 was just a free variable that we can choose freely, right? So in other words, we didn't have any equations like x3 equals something, right? Because x3 is literally a free variable that we can choose with the any values, right? But in order to form this solution vector that contains our free variables as well, for this x3, we can just write it as an x3, okay? So far, it's a quite simple tree, right? And then this is our solution vector, right? And then next thing that we can do is to factorize it into this form, where we have our free variable here, and then some column vector here, okay? So we factored it out, and then 0 can be factored into x3 times 0. And what about x3? So it will be just factored out into x3 times 1. Okay? So this is our solution vector, and the new kind of representation in a single vector form of our solutions, right? And then it means, it means like this guy, this vector times x3, and x3 again was our free variable, so we can choose freely this variable, right? And then this representation gives some kind of new perspective or interpretation of our solution. So let's look at our solution vector x1, x2, x3 as some vector living in three-dimensional space. So we think of, or we imagine the entire three-dimensional space, okay? In this three-dimensional space, our solution is represented as this form. That means it is a scalar multiple of a particular vector. And that vector is, that vector has a particular direction, right? What was the direction? The direction was 4/3, 0, 1. So that will be our direction, okay? And then we can freely choose this value, that means we can stretch or shrink the length of this vector along the same direction, right? Okay, so this is our solution set, right? And also this means that, starting from this homogeneous linear system where we have all zeros on the right hand side, okay? And then we always guarantee that we have a zero as our solution. And can we create all zero solution from this form? I mean, can this vector be just all zeros? In that case, what will be our x3? x3 will be a 0, right? So that, so this solution is of course included or contained in our solution set, but also by changing x3, our solution is actually along this particular line, right? So this is the three-dimensional space composed of these x1, x2, and x3, and then this direction or this v vector was our 4/3, comma 0, comma 1, okay? And then we had a free variable x3, right? And so we can freely change this, and then all the points along this line will be our solution set. And that means we have infinitely many solutions, okay? Infinitely many solutions. And thus, in this case, whether we have a unique solution of all zeros or we have infinitely many solutions. So that is determined by whether we have a free variable or not. Okay. So again, if we have a free variable, and then we can form our solution vector in this form, okay, and that means by changing our really the free variable with any values that we want to choose, and then we can have a many different solutions or infinitely many solutions. Okay, so having the free variable is the same as having infinitely many solutions for this particular linear system, which we call homogeneous linear system. Okay. Okay, and then this kind of a representation or this way of representing our solution is actually called parametric vector form or parametric vector equation of our solution. Okay. Okay, so what is U and V and S and T as well? Okay, so in this case, this is our vector U that specifies the direction of our solution set. Okay, and then this is a in boldface, and then this is our parameter that we can freely choose. Okay, so that way we can represent it as maybe T. Okay, by just rewriting x3 as t, and then this vector as u. Okay, and then let's see. What if we have like two free variables? Okay, so what if we have a two free variable? In that case, those two parameters of our free variable will be corresponding to s and t, and then that will also have this specific vector that has a specific direction. Okay, so you'll be able to see this by looking at some other examples as well. But let's just focus on this original example where we had these coefficient part and zero part. Okay. So this was what we call homogeneous linear system. And then now let's think about a new linear system where we have exact same coefficient but different b part, which is no longer 0, right? So in this case, this was a homogeneous linear system that has all zeros on the right hand side, but we don't change at all on the left hand side. But suppose we change it the b part as some non-zero value. Okay, so let's consider that equation or that linear system. So again, this left hand side part will be the same, but the b part is now a certain vector that is no longer be a 0 vector, right? Okay, so in this case, yeah, as I mentioned, or as we looked at this example last time, once we change it into our reduced echelon form, okay, reduced echelon form, and then we have a pivot and pivot here. Okay, and then we have some b vector over here. Okay, but what about this part? This part. This part will exactly be the same as this homogeneous version of our linear system. So this was our homogeneous linear system, and then it's a little dirty. So let's see. So if we look at this part, and then this part will be exactly the same as this part in our slightly different linear system where we have a, where we started with the different b part. Okay, so as long as our coefficient part for this one was the same, okay, and then regardless of what particular b vector is, our reduced echelon form will at least have the exact same part for this guy. Okay, so once you do some exercise, or you may have already did some exercise on this row reduction, and then you can easily understand that. Okay. Okay, and then here, let's look at its parametric vector form, or the solution, or the representation of our final solution in this case. So what we do in this case is the same as the previous case where we did where we moved all the free variables to the right hand side. Okay, so we move our free variable corresponding to this guy into this right hand side. Okay. Okay, and then we have a free variable x1 represented here, and then x2 will become now 2 because we had just a free variable in this second equation, but previously this guy was 0, but this guy is now 2, and thus this one will be the new value for our second variable, and then x3 is still a free variable, right? And then in this case, let's try to represent our solution vector similar to the previous case. So what I mean is that, so we want to form this kind of vector representation for our entire solution. Okay? Okay, so this is our final solution, but we will form this entire solution vector, and x1 will be having this form, x2 will be 2, and x3 was our free variable, and thus we just write the free variable as it is. Okay, and then from here we separate it out into two parts where we have this constant value here, and then this part containing our free variable. Okay, so in this free variable part, we can factor it out into this form. Yeah, in this form, and then we have a scalar multiple of an x3. Okay, and then we have this new vector that contains only the constant values. Okay, only the constant value. So where did this vector come from? Okay, So let's try to compare this case where we had a non-zero values for our B part, and also it's a homogeneous version of the linear system. Okay, so in that case, since this part was the same, okay, since this part was the same, this part, okay, this part will be the same as the homogeneous linear system, but we now have this new additional constant vector. And where did this guy come from? This guy was coming from here, right? So here, previously we had zeros. Okay, so we had all zeros in this case, right? So it didn't have any additional kind of constant vector other than just a zero. But in this case, we now have a non-zero vector here in this case, right? And then that will be our new constant vector that is added with our free variable part that is corresponding to this guy, okay? But this guy is actually the same as the previous homogeneous case, right? Because, I mean, the reason is because we will have this part, okay? This part to be exactly the same as its a homogeneous version of this part, okay? So, the only difference is the B part, non-zero B part, okay? And then, so we considered this form, okay? So this form. So this is our entire solution set. So we have a specific direction of 4 over 3, 0, 1, okay? And then we can freely change x3. That is corresponding to a single line crossing our origin, right? So we are crossing or passing through our origin, and that with that specific direction, okay? But in our non-homogeneous version of our equation, we have a non-zero vector on the right hand side, and then the solution is almost the same, but we have this new constant vector, right? And then this part will be the same, right? And so, how can we interpret this representation? Okay, so here again, this x3 is our free variable that we can really change. Okay, and then this has the specific direction of this vector 4 over 3, 0, and 1. Okay, but it is added with this constant vector. So it is it is like, so when x3 was 0, okay, when x3 was 0, the previous case, the previous homogeneous linear system, what was our solution? It was like 0 times this vector, and thus it was just simply the origin. So origin was the solution vector when we chose our free variable as 0. So again, if we choose our free variable as a 0 value, and then this is our solution, right? And then in this case, what is our solution when we set our free variable as 0? That is simply this guy, -1, 2, and 0, which comes from here in this vector, right? And thus it's like translation or moving this point to a new point of -1, 2, and comma, but the vector direction or the direction of this line will be the same. So it's like parallel shifting, okay, of the previous line, so that it can pass this particular point. Okay, so let's look at this figure. Okay, suppose in this case where p is 4 over 3, 0, 1. So this was our particular direction. And then previously, our homogeneous linear system had a solution along this line, right? But in our new linear system where we had a non-zero b, and then this origin is moved to a new vector which corresponds to like this guy, negative 1, 2, and 0. So this guy is negative 1, 2, and 0, right? But passing through this point, but the line will be still like parallel because we are adding x3 times this vector, the same directional vector, right? Okay, so yeah, again comparing like this form and this form. So this is the only difference, and that works as like shifting or moving our origin into a new point. Okay. So that kind of parallel movement of a particular line, okay, and that is called a translation. Okay. So parallel movement of the previous line, or maybe some other curve, okay, and that is that is called a translation. So what is it called? What is this translation called in Korean? 네, 네, 이거 평행이동이라고 부르죠. 네. 그래서 결국 원점을 지나는 어떤 직선이 있었는데, 네. 근데 그게 호모지니어스 리니어 시스템에서의 솔루션이었다면, 이제 호모지니어스 리니어 시스템이 아니라 이제 B 파트만 싹 이제 어떤 난제로 값으로 바뀌면, 그때 솔루션은 아까 호모지니어스 리니어 시스템의 어떤 그거가 이제 원점을 지나는 직선이었다면, 이제 새로운 리니어 시스템의 솔루션은 그 어떤 같은 방향을 가지되 이게 어떤 형태로 이제 평행이동이 된 어떤 그런 버전의 솔루션으로 나타난다. Okay, so yeah, this is a kind of similar figure. So we have a homogeneous version of the linear system, and then we have the maybe non-homogeneous version of the same linear system. Okay, so again, the solution set of this guy and this guy, yeah, will be just different in terms of their like parallel movement. So one will be the parallel movement, parallelly moved version of the other one. Okay, and then in this case, this guy is always passing through our origin, right? Okay. And then, so we have the theorem 6, and this theorem 6 is kind of important. Yeah, it's important, and it's a little bit insightful. So, yeah, I also often gave the exam problems related to this theorem. So please pay attention to understanding this theorem. So let me explain this theorem. Okay, so this was our solution, right, for our homogeneous linear system. And how we interpret it is as follows. So it passes through this point, and then also it has this particular direction, right? Right? So it's something like, so we have this particular point on the line, and then this guy is specifying the direction of our line, right? So that guy is specifying the direction, and this guy is specifying a particular point that our line passed through, right? But what about slightly different form, like what about this form? So this form and this form is actually exactly the same line. So this is my point, and let's try to understand that. Okay, so this guy is like passing through this particular point and having this specific direction for our line, right? And then those two representations are exactly like equivalent to each other. So how can we show that these are equivalent? Okay, so here x3 and x3 are just free variable that we can freely choose, of course. And then let's just slightly change this as this guy. So this guy is maybe x3, and then this guy as maybe x3 dash. Okay, this is a slightly different x3 dash. Okay, in this case, if x3 dash as x3 as this guy, okay, in this guy, in this form, let's just plug this guy into this form. Okay, no, it is not 1, it is 3. Okay, and then once we plug this guy into this x3 dash, okay, and then it will be like x3 times this vector, right? And then minus 3 times the same vector as 4/3 and 0, 1, right? And then this guy will be minus 4, 0, 3, right? And then this 4, 0, 3 is subtracted from this guy, okay? And then the resulting vector will be -1, 2, and 0, right? So this version and this version, I mean these two different representation, has the just a small difference, that this x3 prime is nothing but x3 minus 3, okay? And the point here is that x3 and x3 prime in these two different equations are just a free variable, okay? So we consider all the possible values for x3 and x3 prime or x3 dash, and then just collect all these possible points, right? And that will form a particular line, and this one will also form a particular line, right? And these two lines will still have the same direction. And then this guy, the first part, this guy and this guy. So those two are just nothing but just one example point. So one of the many points that our line passed through. Okay, so that way, I mean the same direction, and then I give just one particular point along this same line, and then eventually, after changing x3 or x3 dash with all the different values, and then collecting all the points, and then those collection of points will form the exact same kind of a line, right? So can you guys understand this? Okay. Okay, and then so this is let me give a kind of a simpler case. which is kind of a more familiar version of the example. So in this case, suppose we consider this line that has the slope of an a and then b as a kind of y-intercept, right? So if we think of like 2x plus 3, and then it's like it's passing through 0, 3, right? 0, 3, and then the slope is what? 2, right? So this is 2x plus 3, right? And then here, let me give one version of the clues that we can form this same line, where I give this information. Okay, the slope is 2, and one point that this line passed through is 0, 3. And then collecting or utilizing these two information, we can easily form this line, equation for this line. Or let me give another version of the clues. So we still have the slope as 2, but I'm going to give you another point. Now, instead of giving this point to you, I'm going to give a new point of this point. Okay? So in this case, how do we form the line here in this case? So we have y minus 7 and 2 times x minus 2, right? So in this case, 2x minus 2, 4 plus 7, and thus 2x plus 3, right? So that way, once we specify the same direction, okay, by using the same slope, but I gave you just a different point along this line. Among many points along this line, I just gave you 2 different points, right? But still, they will form exact same kind of a line equation, right? So this is a kind of a corresponding to this a simpler example, right? So this is almost the same. Okay, so here in this case, the previous exam question was something like this. So in our homogeneous linear system, suppose we had this guy, 1, 0, and 4 over 3, and 0, 1, 0, and 0, 0, 0, and 0, 0, 0. So this is exact same example that we saw. Okay, and then in this case, we know that x1, x2, x3 is the x3 times 4 over 3, 0, and 1. So this was our solution. And then now I give you the new equation or new linear system, but I don't give you B, okay? I don't give you B. But here in this case, I just give you just one point, one solution as maybe 1, 2, 3. Okay, that is satisfying our linear system of an AX equals B. And comparing these two, they have the exact same A part but different B part. Okay, and then by combining this fact and this fact, how can we represent the solution for this guy? Okay, x1, x2, x3. So how can we represent the solution of this guy, even without using or even without knowing B part? The solution is really simple. Just I give you or specify just one point that is given here. We don't know how this value was computed, but someone just gave you this particular solution that satisfies our linear system. Okay, so that will specify some particular point, and then also between this and this, okay, between these two different linear systems, we know that they will have the exact same slope. Okay, they will have the exact same form like this. Okay, so finally the answer is just nothing but this guy. So this is our final solution. So yeah, so in this case, again, yeah, I didn't give you what the B value is. Okay, so this is how it. This is the main point of this last theorem in this chapter. Okay. Okay, so for this guy is has the solution. Okay, so that is a kind of a necessary condition. So we need to guarantee that. So this guy has at least one solution. And then this P is actually a particular solution. I mean, yeah, it's an P is an acronym for particular. And that means when plugging P into this equation, it will be true. Okay? So this P is something like 1, 2, 3 that I give you. Okay? So given this P as one solution satisfying our linear system, and then the general solution or the entire solution set of our linear system can be represented in this form. Okay, in this form, it is like P plus VH, and then P is this particular solution that is corresponding to one particular point that our line crosses or pass through. And then what is VH? VH is any solution that satisfies our homogeneous linear system. And what was VH? VH is all the solution of our homogeneous linear system. And what was that in our case? That was this guy, right? So this was the entire solution set of our homogeneous linear system. And so we just simply combined or added this guy with this guy. So that will be our final solution set of this linear system of an AX equals B. Okay? So this is what this theorem 6 is saying. Okay, so in this chapter, yeah, of course, this theorem is a really important one, but also, yeah, one important trick that we studied in this chapter is this guy. So we initially represent our solution in this form, right? And then we convert it or change it into just a single vector form, right? Just listing up our entire variables from x1 through x3, okay? And then for basic variables like x1 and x2, we represent them in terms of our free variables, right? And then for our free variables, since we don't have any kind of equations for our free variable, because we can freely choose any values for our free variable, so we have no equations like this, right? And thus, in order to form this solution vector, for this free variable, we just rewrite once again for this free variable. And then it will be naturally factored out into this form, okay? For our free variable and the specific constant vector, okay? So this is another important trick that we studied today. Okay, so that's it for today. And yeah, thank you very much.
처음에 요거 x3 다시 하신 거 이렇게 이해를 해도 이렇게 원래 그냥 이게 있고 거기 이게 평행에 이동을 했는데
네.
그냥 주어지는 포인트가 그냥 다른 거다.
아, 네. 그러니까 이게 일단 아까 그 두 개 x3랑 x3 프라임 나온 거는
네.
그거는 기본적으로 둘 다 똑같은 라인이에요.
그죠.
네, 똑같은 라인이어서 또 이렇게 네. 여기다 자, 지금 요 라인, 요것도 라인이에요.
네.
이 라인이고 어떤 주어진 한 점이 있고 기울기가 주어져 있는 거예요. 그렇죠?
네.
이것도 마찬가지로 주어진 한 점이 있고
예.
기울기가 있어요.
네.
이거 두 개는 정확하게 동일한 라인이에요.
네네.
그러니까 이거 두 개가 그러니까 예를 들면 하나는 원점을 지나는 거고 하나는 뭐 이렇게 붕 떠 있는 게 아니라
예.
둘 다 그냥 똑같은
네,
라인이에요.
똑같은 라인. 똑같은 라인에서 예시를 든 점이 다른 거죠.
그렇죠, 맞아요. 정확하게 보여요.
그리고 두 가지가 더 있는데
네네.
제가 이게 맞게 갔는지 모르겠어요. 이렇게만 뜨고 퀴즈 제출이.
그 학번을요.
네.
나한테 좀 이메일로 좀 알려줄 수 있을까요?
이메일로?
우리 조교나 나한테 그 공지 이메일에 회신하면은 리플라이하면 그게 되거든요.
네.
네, 그래서 그 이메일로 학번을 알려주면 내가 한번 잘 제출이 되는지 체크를 해볼게요.
알겠습니다. 그럼 교수님 이메일로
네.
알겠습니다.
네.
그리고 나머지 한 개가 홈워크 2가
네.
후반부로 가니까 15번부터인가가 이제 뭔가 이그샘플이라는 게 없고 그냥 쭉 읽는다? 약간 읽어본다? 그건 약간 캡처를 안 해도 되는 건가요? 15번 이후부터는?
네. 그 내가 정확하게 그 문제가 기억이 나지는 않는데
네.
뭐 그렇지 않을까 싶어요.
그러게요.
네.
플롯 이후부터는
네.
그럼 괜찮을까요?
네. 이게 뭐 조교가 이메일을 보냈듯이 이게 뭐 이렇게 정확하게 뭔가 답을 내야 되는 거라기보다는
네네.
한번 그냥 거기에 있는 것들을 실행을 해보고 그게 뭔지 한번 좀 이해를 좀 해보자라는 취지라.
네.
네. 뭐 그게 크게 막 이렇게 뭐 정확하게 뭐 이렇게 좀 여기서 또 코멘트를 해야 되고 뭐 그런 거 아니라서
그럼 뭐
그냥 하면
이걸 해봤구나라는 걸 증명해.
네. 그 정도로 이렇게 그 정도를 보여줄 수 있는 그런 거를 제출하면.
알겠습니다. 감사합니다.
네. 수고했어요.
네.
오늘 배운 게 이제 AX는 제로 이런 이름이 뭐였지? 호모제니어스 리니어 시스템에서 이제 이거를 AX 모양은 똑같은데 이것만
네.
B로 바꾸면 0이 아닌 무언가로 바꾸면
네네.
식이 이렇게 바뀔 수 있다는 B가
네.
이런 거라 했을 때 앞에 B가 이쪽으로 오고 그 다음에 이 원형은 그대로 유지하죠.
그렇죠. 네.
근데 이게 그러니까 흐름대로 따라가니까
네.
이해는 되는데
네.
여기서 만약에 리듀스드 에슐론 폼이 이렇게 나왔잖아요.
네.
그럼 당장 B가 그냥 여기서 예시로 든 1, 2, 3이라고 하면
네.
해가 나올 수 없는 경우가 되는 것 같은데 왜 이런 식으로 해가
네.
뭔가 이해는
네. 그 좋은 지적인데요. 네.
그래서
좋은 지적이고요.
네.
맞아요. 이게 가만있어 보자. 잠깐만요. 그게 그렇지는 않은 게
네.
네. 요 1, 2, 3이 1,
네.
2, 3이 지금 보면 여기 있는 1, 2, 3이어야 되느냐?
그러니까 리듀스드 에슐론 폼
네.
되기 전에 그것이 1, 2, 3이 될 수도 있고
요 1, 2, 3은요. 그러니까 그래요. 잠깐만 이게 그러니까 지금 이 경우도 보면 이 경우를 보면
네.
뭐 굉장히 날카로운 지적이고요. 지금 요거랑이 정확하게 같은 직선이다라는 거는 이해가 되죠.
네.
그러니까 그냥 순수하게 직선의 의미로서
네.
기울기가 혹은 방향이 같고 어떤 지나는 점이 다르긴 한데 역시 여기 위에 있는 어떤 한 점이라는 거니까
네.
그렇죠? 이건 똑같은 거예요. 그러면 거꾸로 이거는 지금 어디서 왔느냐 보면 이게 아까 이쪽에서 왔어요. 아까 이야기한 것처럼 이게 여기에 있는 -1, 2, 0에서 왔는데 이게 지금 만약에 솔루션이 이렇게 나타내줘도 정확하게 동치인 어떤 표현인데 그렇다고 해서 요 3, 2, 3이 3이라고 하는 요 솔루션이 여기에 지금 나타난 -1, 2, 0이랑은 다르잖아요.
네.
그러니까 어떤 한 솔루션이 지금 3, 2, 3이라고 줬어요, 누가.
네.
그렇다고 해서 이 3, 2, 3이라고 하는 게 꼭 이 B 파트에 나타나는 어떤 그 벡터는 아닐 수 있다는 거예요.
그럼 그 경우엔 해가 없는 건가요?
네? 그게 아니라 그러니까 3, 2, 3이라는 솔루션은요.
네.
지금 여기서 원래의 요 어떤 지금 요거는 뭐였냐 하면요. -1, 2, 0이라고 하는 솔루션은 이 프리 베리어블에 얼마를 대입을 했었을 때 그거냐 이렇게 해당 솔루션이냐면 여기를 이제 0을 대입했을 때의 솔루션이에요.
네.
이해가죠?
네.
그러면 프리 베리어블이 싹 이제 없어지고 혹은 0이 되면서 요 값이 지나는 포인트가 실제로 우리 어그멘티드 매트릭스에서 이제 리듀스 에슐론 폼을 만들었을 때 가장 오른쪽에 나타나는 벡터인 거는 맞아요.
네.
근데 어떤 또 다른 점 이거는 이 323은 이걸 기준으로 하면 예를 들면 x3에다가 예를 들면 한 3을 넣었을 때에 그때에 해당하는 솔루션이잖아요.
네.
그렇죠. 그렇기 때문에 요 3, 이 3이라고 하는 거는 아까의 그 저기 어그멘티드 매트릭스에서 리듀스 에슐론 폼에서의 오른쪽에 나오는 어떤 벡터랑은 다른 벡터잖아요.
네.
그리고 이거는 이제 x3를 내가 난제로, 그러니까 0이 아닌 어떤 특정한 값을 조절했을 때 나온 어떤 벡터잖아요.
네.
그러니까 요거는 실제로 솔루션이긴 하나 이게 실제로 어그멘티드 매트릭스의 가장 오른쪽에 나타난 컬럼이 지금 아닌 거죠. 그래서 여기서 내가 1, 2, 3이라는 하나의 솔루션을 줬다라고 했을 때 이게 우리가 이런 식으로 파라메트릭 벡터 폼으로 나타냈을 때 이 프리 베리어블을 실제로 0으로 세팅했을 때 나온 솔루션이냐 혹은 이 값을 적절히 다른 값으로 바꿨을 때 나온 솔루션이냐, 네, 그런 측면에서는 이게 꼭 이걸 0으로 세팅했을 때 나온 솔루션이 아닐 수 있기 때문에 따라서 이거가 실제로 우리의 그 어그멘티드 매트릭스에서의 그 B 파트에 해당하는 솔루션, 그러니까 그 리듀스 에슐론 폼을 만들고 나서 B의 가장 마지막에 나타나는 컬럼이 아닐 수도 있는 거예요.
근데 그러면
네.
이제 이게 될 수도 있고 아닐 수도 있는 상태인데, 그러면 B가 모든 숫자, 예를 들어 여기
네.
이게 아무 숫자 그냥 X, Y, Z 아무거나 집어넣었을 때
네.
B가 될 수 있는 건 아니고 B가 될 수 있는 숫자들의 조합에도 조건이 생기지 않나요? 얘들 상관관계.
네. 그러니까 이게 B가 뭔지는 몰라요 지금. 근데 거꾸로 이거를 지금 만족하는 어떤 그러니까 1, 2, 3이 그러니까 요 방정식을 그러니까 1, 2, 3이라는 솔루션을 여기다 집어넣으면 그게 만족이 된대요. 그걸 누가 이야기를 해줬어요.
아까 기울기 저런 거
네.
예시로 드셨던.
네. 단서를 그냥 요거 하나를 준 거예요.
네.
그러니까 B는 내가 모르겠는데 일단은 이 지금 방정식이 이 방정식의 솔루션 중에 하나가 1, 2, 3이라고 하는 솔루션이더라.
그러면 그러니까
네.
이제
이게 지나는 포인트 하나고
된다 하면 이런
네.
식으로 나타낼 수 있는데,
그렇죠.
그런 말이 없으면 이제 B에 그러니까 모든 수가 B가 될 수 있다라고 말을 못 하죠. 해가 존재하려면. 해가 무수히.
네네, 맞아요. 그러니까 이거는 지금 해가 지금 존재할 때의 상황을 지금 따지는 거예요. 그러니까 무슨 소리냐면 이게 어떤 여기서의 하나의 솔루션이다라고 누가 얘기를 해줬어요.
네.
그 말은 이거에다가 1, 2, 3을 X자리에 넣으면 이게 만족이 된다는 뜻이니까 이 말은 일단은 해가 하나 이상은 있는 거예요, 지금.
네.
네.
제가 이해했는데 제가 헷갈렸던 게
네.
이제 그냥 저는 이거 배울 때
네.
에슐론 폼 이제 만들어져 있는 거 보면
네.
이제 이 공식을 항상 사용할 수 있으면 바로 빠르게 이렇게 만들 수 있으니까 했던 건데,
네.
그거 자체가 일단 해가 여기 된다는 전제 조건이 있어야 돼.
네, 맞아요. 네, 맞아요. 네.
별거 아닌데 이거
이거 나한테 혹은 우리 저기 조교 이메일 우리가 공지 이메일을 받았잖아요.
네.
거기 이제 그 중에 하나에 이제 리플라이 혹은 회신을 해갖고요.
네.
회신을 해서 저기 그 학번을 좀 알려줄래요? 여기 지금 계속 이렇게 나타난다고 지금 이야기를 해주면서 학번을 좀 알려주면 우리가 좀 체크를 좀 해볼게요.
네. 근데 그 퀴즈
네.
이거는 뭐 앞으로 하는 거예요?
네.
뭐 어떤 거예요? 설명을 제대로 못 들어서.
네.
그러니까 이거는 뭐 평가에 들어가는 건가요?
네. 평가에 들어갈 예정인데 지금 이렇게 된 게 하여튼 뭐 그 학생들 저기 학번을 좀 나한테 보내줄래요?
네네.
네. 지금 이렇게 지금 된 게 좀
네.
이게 제대로 이제 퀴즈 서브밋이 됐는지 좀 확인을 좀 해봐야 될 것 같아요.
네.
네.
이건 뭐 퀴즈는 어떤 주기로 풀어야 되는 거예요?
네?
그러니까 뭐 퀴즈 문제 계속 나오는 거예요?
네?
몇 문제나 풀어야 되는 거예요? 이거?
응?
그러니까 뭐 몇 문제씩 풀어야 되는 거예요?
지금 여기는 3문제 있었죠?
네.
네.
3문제
앞으로 더 퀴즈가 나오느냐?
네네네.
뭐 나올 가능성도 있어요. 네.
근데 이거 계속 이어면만 만든 책.
그러게요. 그거를 그래서 좀 이메일을 좀 그냥 이메일에 저기 학번을 좀 알려주면 이메일로 네. 학번을 알려주면 우리가 좀 체크를 좀 해볼게요.
네네네. 학번 그럼 메일로 보내드리는 거예요?
네. 그 나나 아니면 우리 조교가 이제 이메일을 그 공지로 아마 보낸 게 있을 텐데
네.
그거에 회신을 해서
네.
리플라이를 해서 학번으로 알려주면 될 것 같아요.
아, 네, 알겠습니다.
네, 그럼 내가 한번 체크해 볼게요.